As usual, interrupt me with any questions. We are going to be touching quite a few different things today, so feel free to interrupt me whenever. All right, so first off, Bayesians versus frequentists. These are just two of the most popular statistical frameworks, and it's just good to be aware of what those frameworks are. First of all, frequentist stats is actually the framework that we have been working under mostly when we've been talking about statistical tests, and the probability stuff that we were talking about at the very start of the phase. Those were all frequentist frameworks. And what that means is that when we're talking about probability in a frequentist framework, we are talking about relative frequencies, which is why frequentist. So for example, if you are trying to look for the probability of rolling 1 on a dice, you're actually going to, the answer of 1 out of 6 arises from, the thought of, I'm going to run this experiment an infinite number of times, and then just taking the proportion of the relative frequencies, 1 is rolled 1/6 out of all the times, which is why you end up with that probability of 1/6. So that's a frequentist approach. You have that notion of, you're going to run an experiment an infinite number of times, and take note of those frequencies. Whereas for Bayesians, and we'll see, we actually have sort of touched on a little bit of Bayesian approaches when we were doing probability at the start, but Bayesians like to consider what's known as priors. So Bayesian statistics, they like to take into account other things that might affect outcome. So Bayesian approach comes from this guy, mathematician named Thomas Bayes, and he came up with Bayes' theorem, which we will actually talk about later today. And anything conditional probability can be argued as a Bayesian approach. So we did talk about conditional probability a little bit last week, and just good to know that whenever you see anything with a conditional or anything that has like a prior belief, or like given that something has already happened, what's the probability of this? Those are all Bayesian approaches. This is all very abstract, and just good to know that there are these two main frameworks of looking at stats. Questions about this? Awesome. These are just, again, like I think as an icebreaker question once at a networking event, someone asked, like, are you Bayesian or frequentist? And so if you ever come across such a question, you get to make your decision based on what you align with more. Either is fine. Cool. Next thing I wanted to talk about was the very, very popular interview question. I personally have gotten this question like twice, and because I've been employed, having this question come up twice is a lot. And that is this question. I think especially relevant now, now that we keep talking about like disease tests and like different sort of medical tests and their reliability. This kind of question is, I can predict that. I feel like it's going to get really, really popular. So to set up, and basically you'll see this question with just like different numbers and different contexts, but all work the same way. So just to set up the question, a diagnostic test is advertised as being 99% accurate. And by 99% accurate, it means that if the patient has a disease, they'll test positive 99% of the time. And if they don't have the disease, they will test negative 99% of the time. So this is what it means by being 99% accurate. Sometimes you might have different values within here. So instead of telling you 99% accurate, they might give you different numbers for these. So just something to look out for. And then 1% of all people have this disease. So the question that they're asking is, if a patient tests positive, what is the probability that they actually have the disease? For people who are not as familiar with probability, a very common wrong answer is saying 99%. Just because you say, if a patient has a disease, they'll test positive 99% of the time. So I think a common misconception and a common wrong answer is that the probability that they actually have the disease is 99%. And I'll like draw out the probabilities in a little bit, but the main thing here is that this is the probability of having a positive test given that you have the disease, whereas this is asking for what is the probability of having the disease given that you have a probability test. And so the probability, the conditional probability is actually flipped here. And I think that's what trips a lot of people off. Before I get into like setting up the question, I'm actually going to do it on my tablet. Does anyone have any questions? Awesome. I'm going to share this on a whiteboard here. Can everyone see like my white screen? Cool. Awesome. Let's set up this question. As usual, what I like to do with probability questions, I just like to write everything out, like write all the stuff that I have out. So to start, what are we given? Actually, no, before that, let's define some events. So I'm just gonna call event A having a disease. And I'm gonna call event B testing positive. So these are the two things that you can have. Of course, later we'll see A complement is not having the disease and B complement is testing negative. So now that we have these defined, let's talk about the information that we were given. So information that we were given, 1% of all people have this disease. I think that's the easiest one. So probability of A, which is having the disease, is going to be 0.01 because 1% of all people have the disease. The next thing we're going to set up that we were given is the diagnostic test being 99% accurate. So having that, for example, the two scenarios that they give is if the patient has the disease, they will test positive 99% of the time. So given that they have the disease, they will test positive 99% of the time. I don't know if that made sense the way that I wrote it out. Given that they have the disease, given A, they tested positive B 99% of the time. That's something else that was given. And we can also do the opposite case. Given that they don't have the disease, so A complement, they test negative 99% of the time. So these probabilities are different. I mean, the numbers are the same, but they're describing different things. And what we're trying to find out in this problem is given that you've tested positive, and I'm writing it over here in this corner, hopefully y'all can see, given that you tested positive, what is the probability that you actually have the disease? So this is what we're trying to solve for. We're trying to solve for the probability of A given B. And we were given B given A, and also B complement given A complement, also given probability of A. So this is all the information that we were given. Any questions at this point? All right, cool. Before we get into the question, I wanted to outline two important formulas. So first, the first formula to talk about is Bayes' theorem. And Bayes' theorem, I would say, like, if you're preparing for an interview, it's a good idea to maybe memorize Bayes' theorem. I just have it in my head because I've done it a lot. But Bayes' theorem is that the probability of A given B is equal to the probability of B given A multiplied by the probability of A over the probability of B. So this is Bayes' theorem. It is actually a derivation of the conditional probability formula. So actually we can talk about this super quick. We were given this formula before. Let me see if I remember this. There we go. We were given this formula for conditional probability. If we were to flip the conditionals around, we get this, A intersects B over probability of A. So in both of these formulas, we both have this top part. So if we make them equal to each other and rearrange it, that's how you actually end up at Bayes' theorem. Not super important to know the derivation, but I always think it's a cool one to show. I'm actually going to erase this because it takes up space. All right, so besides the Bayes' theorem, the other one that is also good to know is the law of total probability. I'm just going to call it LTP for law of total probability. And law of total probability is that probability of A is equal to probability of A given B multiplied by probability of B plus the probability of A given B complement multiplied by probability of B complement. As you can see, things to note is that B and B complement will add up to 1. And so the law of total probability can actually be expanded. So if you have, for example, instead of just having B and B complement, if you have like B in like 3 different parts, you can actually expand the law of total probability to having like all your different values of B. If you had like B1, B2, B3, you can expand this and you'll have more terms to add together. But for most cases, for this problem especially, you only need to have B and B complement. Questions about this so far? All right, cool. So let's take a look at what we have and these 2 formulas that we have in our toolkit and how we can solve our problem with what we have. Usually a sign that I want to use Bayes' theorem and maybe the law of total probability is whenever I see flipped conditionals. If I flip conditionals, what I mean is that here I'm looking for A given B, but I was provided with B given A. Just because the Bayes' theorem has this here, has like this A given B, B given A part, whenever I see a flipped conditional, that's a pretty clear sign that I might want to use Bayes' theorem. So all right, let's take a look at what we have and how we can put that together. So it looks like we can actually start with the Bayes' theorem here. So let's actually expand from this, since this is exactly what we want to find. So going from Bayes' theorem, we can have this equal to the probability of B given A, which awesome, we have that as 0.99. And actually, let me just write those numbers instead. We have 0.99 multiplied by the probability of A, which is 0.01, divided by probability of B. Now that we don't have. Probability of B we don't have. Questions so far? Right now, all I'm doing is I'm just plugging in numbers into Bayes' theorem. Awesome. So from here, we have to actually figure out and see if we can figure out what probability of B is. Usually, if I have a bunch of conditionals and I want to find like a sole probability, that is something that leads me to think, okay, maybe law of total probability. So let's try and see how we can use the law of total probability here to find probability of B. So just to make things easier, let's rewrite the law of total probability for probability of B. And really quickly, we'll just flip all the A's and B's around. Plus probability of B given A complement. And let's plug in the numbers that we have. So right now we have, all right, we have B given A, we have this value over here, 0.99. We have probability of A, 0.01, which is great, plus B given A complement, which we don't really have yet, but we have probability of A complement, which is 0.99 because 1 minus 0.01. All right, so the only thing that we're missing now is probability of B given A complement. So to figure this part out, we actually do have this number, but let's really think about what B given A complement is. Probability of B given A complement is the proportion of A complement that is B. That's one way that I like to think about conditional probability, is the proportion of A complement that is B. So due to that, I like to think about, all right, proportion of A complement. What number do we have here that also shows us a proportion of A complement? That would be right here. You can see that here we have the probability of B complement given A complement. So this is the proportion of A complement that isn't B. So something else to remember, or something to be aware of, I guess, is, and let me use like a different color. So, oops, there we go. So something else to remember is that the probability of B complement given A complement plus the probability of B given A complement is equal to 1. Just because we're both looking at, the proportion of A complement, and that is which part is B and which part is not B. So this basically leads us to conclude that we do have this value of probability of B given A complement being equal to 0.01. And so we can plug that in. So we have the probability of B being the complete evaluation of that math. Questions so far? All right, so now we actually have all the pieces of the puzzle. We can put them together. The probability of A given B is 0.99 times 0.01 divided by, and you can sort of see here, this is double of 0.99 times 0.01, which actually evaluates to half. And there we have it. So with these numbers of like a 99% accuracy and 1% of people having the disease, if you get a positive test, you only have 50% chance that you actually do have the disease, which is a far cry from what people would assume, like 99%. So actually now it's very, very relevant. Now you sort of have an idea of, how many people out there in the world have COVID versus the positivity, versus the accuracy rates of the COVID tests. You can really see, like, based on those numbers, what is the probability of actually having COVID given that you have a positive test. And it will also be different. The numbers will work out differently if you get a negative test. But yeah, this is a question that does come out. I think out of all the probability questions, this one is the hardest one, but it is the one that comes up most often because it does challenge, you're thinking about probability, whether, you have the Bayes theorem and law of total probability in your toolkit. But yeah, any questions? Cool. Just as a preview for tomorrow's warm-up question, I'll be posting a variation of this, and I want to see y'all work it out. Cool. Questions about?
I have a quick. The most important thing that I can see here is the first assumption that you made. For example, A as a disease and B as a test positive.
Yes.
Any recommendation on that? Because I mostly does that wrong.
Yeah, I think here you have the way I think about it, and the way that I help, like the mindset that I have that makes it easier to set this up is there are two separate things going on. Like one, there's a disease going around and people have it or they don't have it, but independently there's a test that is positive or negative. There's actually another way of solving this problem. If you were to like draw out all of the, if you draw in like a probability tree diagram, I don't know if anyone's seen those, you can actually find these exact probabilities that way. But was your question about how I decided that A was disease and B was test positive?
Yes, somehow in this case.
Yeah, I think just think about what are the events that are occurring. Usually, I think in good news, usually for this kind of question, it's always about some sort of medical test and like a positive negative result. So because of that, you can always define your events that way. But yeah, I just sort of like to think about what are the two separate mechanisms going on, and also one thing that I don't know if this will help or not in understanding it, but A and B happen independently. Yeah, I don't know if that was helpful or not. It's kind of something that also I will say, unfortunately, does come with practice.
Okay, thank you.
You're welcome.
I had a question as well.
So
if we assigned B as testing negative, would it change the answer?
Let's see. If we assign B to testing negative, I don't think so. Let me see. Yeah, I actually don't think so, because there is some symmetry. There is some symmetry over here. Oops, I didn't mean to erase that. But because of the symmetry around here and here, them being both 0.99, I don't think it'll make a difference. Just because the accuracy rate for testing positive and testing negative is the same. But I don't know, you can work it out and see if it gives you the same result. But my hunch is that it should be the same.
Wouldn't your PA, though, if you're looking at negative results, change? Or if you're looking at like,
Yeah.
if your B is negative, then your P of A changes to 99 instead of 1.
Well, that depends if you also decide to change your P of A into having negative results. So the difference being like, yeah, a little bit trickier, but the difference being instead of this being the probability that you're looking for, you're going to be looking for, instead of that, you're going to be looking for this probability. You're going to be looking for B complement.
Oh, wait, yeah, that makes a lot more sense. Never mind.
Yeah, all good, all good. Yeah, it's kind of confusing, especially when you have to like think about how they interact with each other. But yeah, and it does get a little bit more complicated once this value becomes the one that you want to find. But it works out in the same way. You would instead, in your law of total probability, for looking for B complement, you'd actually have to look for, I think, the probability of B complement given A and the probability of B complement given A complement, which I'm not sure we have. I think in the same way you can actually still find those, but yeah, it will require some like mental gymnastics to remember which one is which, and like changing the letters in the formula. But yeah, good question. Made me think a little.
I had another question. When you were adding up the conditionals to 1, could you do the same thing for probability of B given A complement and probability of B given A?
You mean the red part that I have up there?
Yeah.
So let me see. Your question was B given A complement and B given A, right?
Yeah. Is that also equal to 1?
Yeah, so this one doesn't equal to 1. So that's because here we're looking at what proportion of A complement is B and what proportion of A is B, which is slightly different.
Oh, okay.
Yeah, so imagine if you have B here, and then you have, I guess it might also add up to 1. I have to think about this more. Usually you want, let me see, if this is A, sorry guys, I'm just gonna think through this really quick. If this is A and this is B, the proportion of B that is A complement would be this part. Proportion of B that is A complement would be this part, and proportion of B that is A would be this part. I guess it also, yeah, I guess it does. I guess that does track. Yeah.
So I think it adds up to the probability of B. Instead of that 1, it adds up to the probability of B.
Yeah. Does it add up to probability of B? Because this is looking at a proportion, right? So I can see that this looks very, very similar to the law of total probability here. And for it to add up to the probability of B, you would then have to multiply it by probability of A there and probability of A here. I'd have to think about it more. But I think there are some specific conditions that do have to be met, to be honest. But good question. Yeah, I'll have to think about it some more and then let y'all know. Thanks, Matthew, for that. There are probably formulas that exist somewhere, so I'll Google them real quick later on. Anything else? Wanted to talk about MLE, which is, or actually before that, I wanted to talk about the Monty Hall problem really quickly.
Can I just comment on the B given A right there?
Yes, please.
When I go through it in my head, I use like the words. I say, what's the probability of testing positive if you don't have the disease, plus testing positive if you do have the disease. So in my mind, that's all of the possibilities of testing positive. So B is equal to 1 in that scenario.
Yeah, that makes a lot of sense. Yeah.
Am I right?
Yes. Preliminarily, I will say that is correct. That this formula does hold. Yeah, we'll say that this does hold for now, but I will double check and send a resource if I find one. Yeah, but what you said makes total sense. But cool. Any last questions? I do want to move on from this really quick.
And when we exactly have the probability of 1, for example, probability of A union probability of B is 1, or probability of one of them is 1?
In this question?
Yes, for example, in the circles below, for example, probability of A union probability of B is equal to 1. We can say that or not?
No, I don't think we can say that. We can say that the proportion of this part and the proportion of this part out of B will add up to 1, but this exists in some bigger world that we are not sure what those probabilities are. So we can't exactly say that the union of this equals to 1, no. But these are all good thinking questions. I know that was not super helpful, but thanks for that question. Okay, cool. I do really want to move on and talk about the Monty Hall problem super quickly. I'm going to keep this whiteboard up and set up the Monty Hall problem super fast. Here are all drawings. So the Monty Hall problem is basically you have 3 doors. I think I talked about this really quickly when we were talking about probability, but in a game show, you have 3 doors. Behind one door, you have a car, and behind the other 2 doors, you have goats for some reason. And of course, you want to win the car. How the Monty Hall problem works is, as part of this game show, you first choose one door to get the prize behind that door. And after you've chosen that one door, the host will open another door showing you that there's a goat behind it. And so that rules out that door. And the question is, should you then switch your door to the last remaining door, or should you keep the door that you have? Does anyone need clarification on that setup? There's also an entire lab talking about this, but I just wanted to share one of my other ways of breaking down this problem. In the lab, you're actually asked to run a simulation of like switching your door versus keeping the door and looking at your probability of winning. And what that shows is if you switch the door, you actually have a double chance of winning versus keeping the door that you have, which I think for some people might be counterintuitive because, you know, first you have a 1/3 chance of your door being correct. If he's ruled out one of them, your chances become 1/2, which is higher. So I think that is the part that makes people think that maybe you should keep the door, but it actually does work out to switching the door. There's a way of doing this using Bayes' theorem. I personally don't like that method of solving it because I'm of the mindset of if you don't have to use a formula, don't. So I wanted to share my way of solving it, which I think I learned from the YouTube channel ASAP Science. I don't remember. It's one of those YouTube channels that I saw the solution and I thought it was really smart. And it's very similar to the way I like to solve other conditional probability questions. If you came to the probability session we had at the start of the week, I like to just have everything out in diagrams so it's easier to see. So the way I set this up is I like to think about it as actual versus choice. So in terms of actual, your prize could be behind door 1, 2, or 3. And with your choice, you could also choose between doors 1, 2, and 3. So let's take a look at what you should do in each situation. Let me just make this the same. So, all right. So if the prize is actually behind door 1 and you choose door 1, should you stay or should you switch? If the prize is actually behind the door you chose, you should stay. Oops, why does it always go to, there we go. You should stay. Very similarly, across the diagonal, if the prize is behind 2 and you chose 2, same with 3, you should stay. And now with all of the other situations, if, for example, the actual prize is behind door 1, but you chose door 2, you should switch. And basically, for every other combination, you should switch your choice. And all of the possibilities are already on this table right here. You can see that if you were to stay, you have a 1/3 chance of winning. And if you were to switch, you have a 2/3 chance of winning. And that, I think, is just a simpler way of doing these probabilities other than using a convoluted Bayesian formula. Just want to share this. This is not super relevant to our material, but I thought like an easier way to solve it. Questions about this? All right, awesome.
I have a question.
Mm-hmm.
If you switch, do you for sure get the, you don't for sure get the prize?
Yeah, that's right.
So how does it work out that switching is more likely to get it?
So if you switch, so let's say you chose door 2. So if you chose door 2 and the actual prize is in door 1, the door that will be revealed by the host is door 3. So door 3 is going to be revealed. Therefore, when you switch, you will definitely get the prize. That makes sense?
Got it. Thank you.
You're welcome. Yeah, it also has to do with the fact that you know it rules out one option when you switch. Cool. All right. The next I'm going to talk about maximum likelihood estimation. That really sets up what we're doing over the next like 2.5 phases. It's very mathematical, but I think just conceptually good to understand what MLE is all about. So MLE stands for maximum likelihood estimation. And so the keyword here is likelihood. In the formal stats world, the word likelihood means something different from probability. Probability is what we're used to. Likelihood has a different meaning, and I'm actually going to draw those out. So on this whiteboard, I'm going to just divide it into half. On one side, I'm going to talk about what probability is. And on this side, I'm going to talk like, is that how you spell likelihood? Oh, with an E. There we go. Likelihood. There we go. Okay, so first, just to recap probability, and I'm going to talk about probability in terms of a PDF. So let's say we have this distribution over here. Doesn't have to be normal, but normal's just easier to talk about. Let's say we have mean of 20, standard deviation or variance of 4. And the way that we read probability is if we have this distribution, let's say we have this particular point over here, and this is 24. The probability of your value being 24 is this probability 1 here. This should be clear, is sort of what we talked about at the start of the phase. But in a PDF, If you want to look up the probability of value, it's just the probability shown on this graph here. One specific way to write this out is the probability of x, and of course this label x, equals to 24, given that we have this distribution of x being a normal distribution of mean 20 and variance of 4 is equal to this P1. So because we have this underlying distribution of, and this is just a notation for a normal distribution of a mean of 20 and a standard deviation of 4, given that we have this distribution, the probability of x equal to 24 is this probability 1. Anything to clarify here? Awesome.
Wait,
oh, yes.
Don't we actually have to take a range because it's continuous?
Yes, absolutely. Yes, you are supposed to take a range. So technically, yeah, we'll be like x between like some range around 24. But just to simplify, let's just imagine this is okay. Doesn't really matter for this case, but yes, very important to remember for continuous variables, you do want to take a range. But for this purpose, less important. But thanks for bringing that up. Any other things to clarify about this? All right. So likelihood is a little bit different. The thing about likelihood is sort of used to estimate your population. So the way I like to draw it out, and by the way, this way of thinking is taken from StatQuest. So shout out to StatQuest for that. And if you want like another round of explanation of this, definitely check out the video. So likelihood is saying that, all right, if I have this point here of 24, what kind of distribution would I have? And the context of using likelihood is really for inference. A lot of this time we were talking about inferring parameters like, all right, the mean of the population is something or the other. And it's actually a very big part of modeling as well. So in context, so imagine I have like a pet store. And using the pets that I have at my pet store, I want to extrapolate the parameter values, the population parameters of the population of puppies. So let's say I care about the weight of puppies. And in my store, I have 10 puppies. Can I use my 10 puppies to estimate the population's weight of puppies? That makes sense? So we're now, in this case, we're going from small to big. I want to use the sample of puppies that I have, these 10 puppies, and I want to use the weights of these puppies to try and make some inference on what the population of puppies' weights looks like. Cool, so that's what we're gonna do in likelihood. So in likelihood, it's kind of the opposite conditional formula. So given that we have this 24-pound puppy, I don't know if that's a lot or not. Here we have this distribution. So let's just imagine, all right, let's just guess that puppies are distributed this way. And just for the sake of comparison, we're going to estimate and we're going to guess that, all right, maybe the population has a normal distribution of centered at 20 with a variance of 4. The way we write this out is the likelihood. Sometimes you might see P for probability, but to be more specific, we can use L. The likelihood of X, the weight of puppies, following a normal distribution centered at 20 and variance of 4, given that we have this puppy of weight 24, is equal to probability 2. And let me actually draw that out. So probability 2, oh no. Probability 2 is this probability right here. Probability 2 is right here. So the likelihood of this being the distribution of puppies in the population based on this one puppy that I have is that probability 2, which is, I mean, based on this normal distribution, not super great. So throwing the question back at you guys, if I just have this one puppy of 24, what is the best estimate that we can come up with now of the distribution in terms of like the population parameters?
We'll probably guess the mean, median, and mode are 24.
Exactly, yeah. So given that we have this puppy at 24, it would make more sense to guess that, all right, I have this one puppy. I have no other puppies in my store currently. And I really don't know, I guess in this case, I assume I have no idea what puppies are like outside of my store. The best estimate would be a distribution that is centered at 24. Of course, imagine that it has the same height. I don't know if this is gonna erase, it's gonna erase the whole thing. All right, let's just draw this nicer. All right, so it would be a better estimate to estimate that the puppies have a mean. Sorry, that the distribution is centered at 24, because you see here, P2 is higher. So the way we write that out is the likelihood of X having a distribution of 24 and standard deviation of 4, given that X is equals 24, is equal to probability of 3, which is greater than probability of 2. So this is the idea of, we're trying to figure out what sort of curve best fits our data. So that's kind of like the big overarching concept here. We're trying to figure out what distribution best fits our data. And that's the whole idea where modeling comes from. We want to find models that fit our data best, that models our data best. And with linear regression, we'll talk about that in context tomorrow as well. So, all right, let's expand from 24 puppies. So let's say I've got like puppies here, 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 and like further out, a little bit further out. It gets more sparse as we go further out. I'm just drawing this for convenience. Does look like that this distribution fits better. So what we're doing here is we're just trying to maximize the probability, or we're trying to maximize the likelihood of the distribution given our data. So given more points, and there's a lot of mathematical formulas that you can do to derive this. Based on this, typically the population parameters you can estimate by using the mean of your sample. So a good estimate for the mean of your population is the mean of your sample. For standard deviation, it's slightly different. I honestly don't remember it off the top of my head currently, but I have a reading saved that I can send out for those of you interested. But yeah, does that make sense? Here we're trying to find the best curve to fit our data, such that this likelihood, these probabilities here, are maximized, which is why we call it maximum likelihood estimation. And what we'll be doing for pretty much the rest of this course is looking for models that model our data best. Cool.
In this case, is the 20 and 4 point, that's your prior belief?
Oh, you mean these points here?
Yeah.
Yes, so your data would be your prior, because given that you have these data points already, what would your population distribution look like? Yeah, so it's pretty much a reverse of probability. On top of this, there's also odds. Like, what are the odds of this, which is also different. For those of you who gamble, you might understand more, but odds is also different from probability and likelihood. And we'll actually get into that around the start of phase 3. Cool. I will say, like, if all of these things don't really make too much sense, just think of likelihood as you're trying to fit the best curve to your data. I personally think that that is one of the more important takeaways of maximum likelihood estimation. Cool. Any other questions about this?
For every observation, we have to draw a unique distribution based on these topics.
So let's say I start with one puppy at 24, I would center my distribution at 24. As I get more observations, I can adjust my best fit population based on the sample data that I have. Is that?
Oh, okay.
Yeah. So let's say I start with 24, and then I get like a bunch of puppies that are like 22, 23, 25, 26. And then I can basically recalculate the mean of all of the puppies and then just refit the curve to get a better estimate of the population.
Okay, thank you.
You're welcome. Any last thoughts about this? Haha, population, that's funny. All right, so let me reshare my browser real quick. All right, last thing I wanted to talk about, and this we will come back to in phase 3 when we talk about the specific algorithm that uses this, which actually is multinomial Bayes. Basically, multinomial Bayes, what it's used for is for classifying things. The whole of phase 3 will be classification algorithms, and multinomial Bayes is one of them, which you can basically classify things based on their prior probabilities. What I wanted to point out here is that maximum a priori estimation has this reinterprets the Bayes theorem formula as this, as posterior likelihood times prior over evidence. Why I bring this up is because sometimes you might see probability questions, less so in a data science context, I will say, but more so if typically if you want to go for roles that require more like mathematical research, they might ask you, all right, in this situation, what is the posterior, what is the likelihood, what is the prior, what is the evidence? So yeah, just wanted to make note of that, that these are the definitions here. Based on how you set up the formula, what letters you're using, just know that this part here will be likelihood, bottom B will be the evidence, A is prior, and what you're trying to find is the posterior. These are just definitions. I, to be honest, often mix up posterior and likelihood. I always mess those up. So it's something that like before interviews, I just like look at real quick just to remind myself. Well, cool. For this topic and everything up till this point, there is, something that might be helpful for you all as a resource is on campus, and we don't do this online. On campus, there are actually like assessments, and like they're basically like mini tests that you have to pass a phase. So there is an assessment for this phase, and I just wanted to send it out to you all just to attempt. Some people like to use it as a knowledge check. You won't be graded on it, so I'll just send out the notebook to you all just so you can see like what is being tested, what are things that you should know. Those include statistical testing questions. There is a question, just like the one I said, like which is the posterior, which is the whatever. And I believe there's questions about t-tests as well. So I will send that out to you today as well. Any questions? Cool, awesome. So this wraps up our like statistics section. Tomorrow we finally kick off linear regression, which I'm super excited for. The notebook that I'm going over tomorrow is already up on the study group repo if anyone wants to look at it first. One quick thing that I just decided to change in terms of scheduling. Next week, which is the week before I go on vacation, not really vacation, but you know, stop. Yeah, anyways, one change that I made was I'm actually going to introduce this phase 2 project on Thursday and then do topic 20 on Friday. And that's because everything in topic 20 is more of like optional. If you have extra time, then incorporate into your project. So I just wanted to give y'all an extra day to sit with the project so that maybe when we're talking on Friday, you still have an opportunity to ask me questions. Something else that I want to let you know, you don't have to do this now, but the project 2 guidelines are actually up already. It will make more sense for those of you who have been looking at topic 18, but good to just read over if you want to get a bit of preview of the project. The project is also already up on Canvas, so I think it's a good idea to take a quick look at it before Thursday. Questions on that? Cool. I think having like the gaps between the topics, like we have the weekend between 18 and 19, a couple of days between 19 and 20 will be beneficial so that there's more time for stuff to sink in. But yeah, I will also send out like a complete schedule of instructors that are covering the sessions while I'm gone, just so you have that as well. And let me see if I'm missing anything. And yeah, don't forget about this mini assignment. I will be looking at it before I go, because this is honestly like a really, really good precursor to the project. Pretty much the project will be exactly the same as this appendix project. So you might want to do that. I will say that one is much longer than the topic 18 and the topic 18 project. So it's kind of up to you to decide what you want to do. But yeah, I do see that students who attempt this appendix project have a better, or get into the actual project process a lot faster. Cool. All right, final questions. Awesome, very excited to be done with this stat stuff. And I will see you all tomorrow when we finally get to talk about regression. I do really recommend that you at least look at some of topic 18 before we start tomorrow. All right, well, if there's nothing else, have a good rest of your day, everybody. And I will see you all at one-on-ones or tomorrow. Bye now.